Her work integrates experimental and theoretical research to get a better understanding of the physics of laser matter interactions under extreme conditions and use those interactions to study ultrafast dynamics of matter. Before joining Princeton as a faculty member, she was a postdoctoral researcher at the Max Planck Institute for Quantum Optics in Germany for 5 years and a research scientist at the A.M. Prokhorov General Physics Institute in Russia. She got her undergraduate degree in 2003 and PhD in physics in 2007 from MV Lomonosov Moscow State University in Russia. And I'm pleased to have her with us today. Please be aware that today's talk is being recorded. So if you're uncomfortable with that, please log off. And also it's on an unclassified meeting with lots of people outside the lab logged in. So please be aware of any of those issues. If you have any questions, you can enter them in the chat field and I will read them afterwards. Or if you're having issues with that, just signal to me in any way and you can ask your question verbally. And otherwise, I hope you enjoy the talk and please take it away.
Hi, everyone.
Hello.
Hello? You hear me?
Oh, yes, I can hear you fine.
All right, so my name is Yulia Mikhailova, and thank you for having me here. So my research, and I'm really glad to be able to talk about my research here today. My research is about short-pulsed, intense light-matter interactions. And in particular, I'll talk today about these cool devices called plasma mirrors, relativistic plasma mirrors, and how we can use them to manipulate ultra-intense light. So this is the outline of my talk, overview of experiments, our experiments in my lab, intense short pulse laser interactions with solids and gases, fundamental process behind relativistic harmonics of light from plasma mirrors, from these cool devices, their origin of harmonics, spectral scaling, efficiency limit, conversion efficiency limits. And I'll talk about a way to boost the conversion efficiency of these harmonics by optimizing the driving laser waveforms. I'll also talk about cascaded plasma mirrors and multipass high harmonic generation, and we'll wrap up with conclusions. So let me tell you a bit about my lab and experiments in my lab. We are using a titanium sapphire laser system, a terawatt system. It's a pulsar system from Amplitude Technologies. It's it's a class of systems, pulsar terawatt. Amplitude sold quite some of them in the world. And the system, at the heart of the system is a titanium sapphire oscillator, and it generates very short pulses, less than 10 femtoseconds. And then these pulses are amplified first in a multipass booster amplifier, which also contains a special device, an acousto-optical modulator, which can allow us to control the phase, the spectral phase in our short pulses, short laser pulses. So that's called dazzler. And then this amplified pulse is stretched. So this is a short pulse amplification system, which makes use of stretching. It stretches the laser pulses in order to be able to further amplify them to higher energies without damaging the laser active medium. And our stretched pulses are further going into the regenerative amplifier. It's a linear region. And this amplifier also has another acousto-optical modulator device, which allows us to control the shape of the amplified spectrum and avoid the gain narrowing in amplification process. So this amplifier runs at a kilohertz repetition rate. So we start with 80 megahertz repetition rate in oscillator, and then we have kilohertz repetition rate of pulses in the regenerative amplifier. And we have another multipass amplifier, which can further amplify those pulses to a couple of millijoule energies at kilohertz repetition rate. And then we decrease our repetition rate to 10 hertz, and we have additional multipass amplifiers pumped by powerful Nd:YAG lasers. After several passes of amplification, we finally compress our pulses, our stretched pulses, in a vacuum compressor, grating compressor, which works at 20 terawatts of peak power. And we are getting 500 millijoule laser pulses with 25 femtosecond pulse durations, really short. And these acousto-optical modulators, Dazzler and Masler, help us to get the short pulse durations. And our repetition rate is 10 hertz, which is a quite high repetition rate for a high power laser. So then we, of course, we do all kinds of diagnostics for these pulses, namely we measure the pulse duration. It's a very important parameter for our experiments. And we also measure the contrast using the third order autocorrelator. We measure the temporal intensity contrast of our pulses, which is especially important for laser solid interaction experiments and plasma mirrors, about which I will talk today. After diagnostics, we send our laser beams to experiments. We have some 3 optical tables with experimental setups, and we have a gas filamentation experiment. It's we propagate the laser beam in a tube which is filled with gases. We can fill it with various gases at various pressures, and we study the propagation of high power laser beams in gases for various kinds of applications. We also have a solid target interaction chamber. It's a vacuum chamber where we do solid target interaction experiments, and we generate high harmonics. So this is our solid target chamber. And we also have an ionization grating experiment in collaboration with LLNL and run by Matthew Edwards and Pierre Michel and others. So that's our main experiments today. And so let me talk a little bit about laser solid interaction, relativistic high energy density plasmas we are interested in. So what do we do in this experiment? We take our laser beam and we focus it very tightly with an f2 off-axis parabola. We get intensities of about 5 by 10 to 19 watts per square centimeter in the focus of this laser beam. And then we move our solid targets, for example, glass targets, into the focus of this laser beam. So our solid targets, they can be translated in both directions in order to provide a fresh surface for every laser shot. So this is how the target looks like. This is the target, and this is the microscope objective for laser focus characterization. So what happens when you focus light to these high intensities? The material in the target is ionized almost instantaneously, and plasma is formed highly ionized, dense, and hot. And then we look at the radiation reflected by this plasma. So we look at this radiation, we look at the beam profiles of this radiation at different wavelengths. We put a scattering screen, a Teflon screen, and look at the scattering of this radiation by the screen. We also look at the direct beam and characterize spatial quality, for example, at different wavelengths. And we also measure spectra. So we use two types of spectrometers. One is a visible spectrometer, ocean optic spectrometer, which can measure the spectra down to 200 nanometer wavelengths. So with this spectrometer, we can characterize second, third, and fourth harmonic of 800 nanometer light, right? And then also we can put a metallic foil filter in the beam path. And with this filter, we can filter out fundamental and some harmonics of light and look at the higher harmonics at ultraviolet and up to soft X-rays, extreme ultraviolet and soft X-rays reflected by this plasma or emitted by this plasma. Right, so after the foil filter, we have only higher harmonics in our beam. And to characterize these harmonics, we are using a vacuum grazing incidence grazing spectrometer and an XUV CCD to measure harmonics below 200 nanometers. We also use gold-coated focusing mirror at grazing incidence in order to send those harmonics into the spectrometer. So those harmonics, they are very well beamed, so they go into a very narrow cone. So it's quite a challenge to measure them with a spectrometer. All right, but did we manage that? So we got these harmonics in experiments. So this is the raw image of the XUV CCD. And this is the line out of the spectrum. So these lines is basically a comb of harmonics, integer multiples of our fundamental driving wave. And this is the line out of this CCD image. You can see frequency comb, this spectral peaks with wavelengths from 70 nanometers down to 20 nanometers. So harmonics in this range, harmonics above plasma frequency, which corresponds to the density of electrons in this plasma formed here. So harmonics above this plasma frequency, which corresponds to wavelengths lower than 40 nanometers in our case, are the so-called relativistic harmonics. So these are especially hard to get, or at least to measure. And we are very proud of getting them in experiment and of being able to measure them with our spectrometer. So they have low divergence. So several experiments have shown that these harmonics have divergence of less than 20 milliradians. And so this is why precise spectrometer alignment is required in order to measure them. You cannot put your spectrometer anywhere around the target, so it has to face this narrow beam. All right, so this is the main result of our high harmonic experiment from plasma mirrors. Why that's interesting. So one goal of our work is to use these harmonics as a source of short wavelengths. But also another thing is that by analyzing harmonics, we can learn something about their source. For example, we are really spoiled by the beauty and richness of acoustic harmonics we have around us, right? So it's much easier to get acoustic harmonics than to get harmonics of light. So light has a strong dispersion, refractive index dependence on wavelengths, and needs strong fields in order to drive harmonics. So it's not that easy to get harmonics of light, but we are really exposed well to harmonics of sound waves. And from sound waves, we know that we can easily distinguish the sounds of, for example, saxophone and trumpet, or violin or piano from one another. And this is thanks to unique combinations of higher harmonics in their spectrum. So the same note played on piano or with a saxophone or a trumpet, the same note of the same octave would sound differently, and we will be able to distinguish one instrument from another thanks to the combinations of harmonics. So one note is not just one frequency, but it's a really unique spectrum. So, and here are my favorite jazz composers, Charlie Parker and Miles Davis. All right, another example of harmonics is recently detected harmonics of gravitational waves, and they carry information about a collision between black holes. So our harmonics of light, they carry information about the interaction of intense laser with a solid target and information about this high energy density plasma we are generating at the surface of the target. So they can both be used potentially as a source of soft X-rays and ultraviolet light, but also they can be used to probe the high energy density plasma, which is emitting them. All right, so what are the fundamental processes behind those relativistic harmonics of light from plasma mirrors? So let me show you this cartoon. This is a result of particle and cell simulation of the interaction of the laser pulse with the plasma. This blue color shows the plasma density profile at the surface of a solid target. And this orange color is a laser pulse. And this is the plasma density, number density, and this is the coordinate in wavelengths. So the laser propagates from left to right and starts interacting with this plasma, and you see it perturbs the plasma density and creates some spikes of plasma density in the plasma density gradient. All right, so let's see. What we see here is more and more bunches are formed. They appear and disappear, and new bunches are formed and appear and disappear. And during the interaction of the laser pulse with the this plasma. And what we also see, we see this reflected waveform. So this is the light which is reflected by this plasma. This plasma is dense. It has density above critical density for our wavelengths, so that light is mostly reflected and not transmitted through this plasma. And we see a lot of spikes, electric field spikes in the reflected field. So this is where our harmonics sit. They sit in these sharp spikes. And we see that the spikes are generated by this kind of density spikes, which correspond to nanometer size dense electron bunches formed at the surface of the plasma target. So let's go back, for example, at some point where we start getting this dense bunches, for example, here. I'll stop here. All right, so if we look at this bunch, which has formed in this density gradient at a certain time instant, what we can say about this bunch is that during a short period of time, it's moving with a relativistic speed in this direction, in this specular reflection direction, towards the laser. And its acceleration at this time is purely orthogonal to its velocity. Okay, so it has acceleration along y-axis, for example, and velocity along x-axis. So the situation, this motion of a charged particle when acceleration is purely orthogonal to the velocity, it's a synchrotron-like motion, right? In a synchrotron, electrons move like this. And we know that synchrotron-like motion is famous for its very rich spectrum of emission and very intense emission at high frequencies. So this is what really is happening here. So we generate, our laser generates very short nanometer-sized electron bunches, very dense, with they have density orders of magnitude higher than the initial plasma density. And these bunches, during a short time period, they move in a synchrotron-like manner and then emit high frequency radiation, which we call coherent synchrotron emission, because the trajectory of these electrons resemble the trajectories of electrons and synchrotrons. So our relativistic harmonics is nothing else than coherent synchrotron emission of nanoscale electron bunches in plasma mirrors. So in our tiny devices called plasma mirrors. There is quite some body of work on this model, coherent synchrotron emission. Usually also this process, relativistic harmonics, it was first described by the so-called relativistic oscillating mirror, which is a great model, and it works for some low harmonics, but it has some, it's insufficient to describe very high harmonics and also to describe the interactions in the situations when the interaction is very efficient and there is a lot of transfer of energy from the laser to the plasma. So the relativistic oscillating mirror model does not include the transfer of energy from laser to plasma, so it fails to predict the correct spectral shapes, the correct cutoff frequency, and the highest frequency which are possible to generate with this process. All right, so there is quite some work, but this previous work, it has limited this coherent synchrotron emission model to some special cases of laser solid interactions, to ultrasyn foils or highly oblique polarized incidents. While we have found recently that when the electron bunch width, the width of these electron bunches is treated appropriately, the coherent synchrotron emission model is valid across a wide range of conditions and can be generalized. So we can say really relativistic harmonic emission from plasma mirrors is governed by the coherent synchrotron model. So in short, how the trajectories look like of electrons, of these electron bunches when they interact with the laser. So electrons, this figure shows the trajectory of electron when it of electron bunch when it interacts with the laser. Laser comes from left to right. This line shows the initial plasma surface, and initially electrons stay near plasma. The laser is not strong enough to push them in. Then when the laser becomes strong enough, it pushes them in. The laser pressure pushes electrons a little bit inside the target. Then the laser field, electric field in the laser pulse, it decreases. It goes through a node because it's an oscillating field. And at this time, ions, electrostatic plasma force, they pull electrons back. Electrons pass the equilibrium position, and they go out of the plasma on this left side into vacuum. At least in this simulation, this is a trajectory obtained in a particle and cell simulation. And at this time, it happens so that their velocity is purely orthogonal to the acceleration, and they emit this short burst of high frequency radiation. And yeah, that's two figures just to illustrate the difference between synchrotron emission, which is very directed and very intense, and emission of a linearly accelerated charge or a dipole, which has always a zero intensity on axis corresponding to the velocity of electron. So synchrotron emission is much more intense than the emission of linearly accelerated charge. And we are happy that electrons in our case behave like in a synchrotron, so they can emit intense light. All right, so this is how the spectra of emission of electrons look like. And so this is the spectral intensity. The y-axis is the spectral intensity of our upconverted emission, and the x-axis is the frequency normalized to the laser frequency. So here is the fundamental laser frequency. Here is the 10th harmonic, 100th, and 1000th harmonic. Both axes are in logarithmic scale. And these are the spectra for two different conditions, for different laser and plasma parameters. What's important in this spectrum, you can see that these are spectra obtained in particle and cell simulations. These are not experimental spectrum. So what's important here is that you can see that these spectra are following power laws, at least for quite some time. So power laws, it's a log-log plot. Power law looks like a line on a log-log plot. So spectra follow a power law, that's great. And we want as shallow power law as possible. So the power law exponent, this exponent here, minus p, so intensity is proportional to omega to the power minus p. This power law exponent determines the power per harmonic. It eventually determines our conversion efficiency. So we are very interested in what is the number for p? What is how large is p, or how small is p? So, and this power law exponent, it depends on laser and plasma parameters. So we can say that this power law is a function of laser amplitude, plasma density, their ratio, the so-called similarity parameter, the ratio of the laser amplitude to plasma density, thickness of plasma, angle of incidence, gradient scale length, plasma density, frequency of the laser, pulse duration, carrier envelope phase under the envelope of our driving laser pulse, and the size of our focused beam, the focal spot size also. So there's a lot of parameters which define the power law exponent. And just to remind you, the laser amplitude in relativistic optics, we're usually using dimensionless units for the laser amplitude. We normalize electric fields like this, and we use the plasma density in terms of critical density. So we normalize plasma density to the critical density of plasma. So if we look at how the power law exponent depends on three main parameters, laser amplitude, plasma density, and their ratio, we can see interesting behavior. So for example, we can see that this power law exponent really depends not only on the laser amplitude and density separately, but also on their ratio. And there is some optimum parameter, some optimum value of this ratio at which we get the highest power law exponent and highest efficiencies, highest conversion efficiencies into harmonics. So the higher the power law exponent, the higher the power of harmonic, power per harmonic per generated harmonic is. So we found that this exponent reaches a maximum, which is equal to -4/3, around -4/3, near this range of parameters when the ratio of laser amplitude to plasma density is about 0.25 to 0.5. So somewhere here, this power law exponent reaches the maximum. So if one wants to get highest conversion efficiencies from the process, one should get the laser and the target with this parameter so that the ratio of the amplitude to the density is about 0.5. So this is the fundamental limit set by the coherent synchrotron emission model. It's a promise in scaling. So I'm talking about the scaling because this basically defines, if we want to answer the question, how much can we get from this process? How much power can we get from this process? So omega to the power of -4/3 is a really promising scaling. For example, it allows us for 1 terawatt peak power to be produced for 1 kilo electron volt photons using a plasma mirror driven by a 20 petawatt titanium sapphire laser. So these 20 petawatt lasers are coming. So, and very soon we will be able to test our prediction with this kind of laser. So the scaling extends only to a certain cutoff frequency, it does not extend forever. So the highest frequencies are restricted by the width of the emitting electron bench. I also didn't tell this in the beginning of the talk, but please feel free to interrupt me anywhere. If you have questions or comments, I'll be happy to have any interruptions. So, any questions or comments? All right. So, and then if we are thinking about the cutoff frequencies and where these power laws end, we can look at our spectra in more detail, and we can see that what happens, we have this power law behavior until a certain frequency, which is given by the width of the electron bunch, of the generating electron bunch. So the width defines which wavelengths can be emitted coherently by various electrons in this finite width bunch. And then after this cutoff frequency, which is given by the bunch width, the power law changes to this function omega to the power of minus p minus 2, and this minus 2 coefficient here is due to the loss of coherence of emissions from different portions of this emitting nanoscale electron bunch. And then eventually we have another cutoff frequency, which is given by the laws of the synchrotron emission, and which depends on the gamma factor of relativistic electrons in these bunches. After that, cutoff the spectrum falls off exponentially. So here, this inset shows the distribution of electron gamma factors in this emitting electron bunch against the time, advanced time. And this distribution is related to an instantaneous electron density profile in the bunch. So these peaks are gamma factors of various electrons in the bunch. And we see that there is some distribution and there is some width, some temporal width, which leads to the steeper power law after a certain frequency. So we can summarize it under most conditions. The relativistic harmonic spectrum, spectrum of the bunch emission decays as a power law up to a roller frequency set by the width. And this frequency is given by this expression where the temporal width of this distribution of the gamma factors of various electrons is here. And this is a laser period, and this is a laser frequency. So this spectrum then decreases as steeper power law. It's omega to the minus p minus 2. Because only emissions of electrons within a half wavelength of the leading edge of the bunch coherently add. So this leads to this additional exponent here. And finally, the spectrum falls off exponentially at the cutoff frequency given by the Lorentz factor of electrons. So if we look at this spectra in time domain, if we make a Fourier transform and go back to time domain, we can see that if we filter various parts of the spectra, the radiation comes as attosecond pulses. So this is the intensity as a function of time, and the time is really short here, so 0.01 of the laser period, so it's 1/100th of the laser period, so it's much shorter than the laser period. And you can see that if you filter out some harmonics from 10 to 50th, you can get this kind of pulse. If you filter higher harmonics from 75th to 375th, you get this pulse. If you go even higher to 600th harmonic or 3000, you get this very short pulse. The temporal duration of the pulse depends on the frequency you filter out from the spectrum. The shorter the frequency you get, the shorter the pulse. you get. So the pulse duration really scales down like this with the harmonic frequency. So, and the intensity of these attosecond pulses, it's also a function of our parameters, laser parameter, laser amplitude, plasma density, and their ratio. And if we plot the intensity of the attosecond pulse as a function of A naught over n, the ratio of laser amplitude to plasma density, as we did for the power law exponent before, we also see similar behavior with the maximum in this function, in this intensity, which corresponds to the value of this ratio around 0.5. All right, so that's great. This is what we now know, what we found about the origin, the spectral scaling and efficiency limit of these harmonics, of relativistic harmonics. Now, I need to tell you that with our current technology, with what we have in the lab, our efficiencies are quite low because our A naught over N ratio is far from 0.5, from this optimum 0.5. So it's more like 0.01. It's more than order of magnitude less than that. So efficiencies at that value of that ratio are not really high. So you need to have higher laser intensities to get higher conversion efficiency. So this is why we are looking into ways how to boost the conversion efficiency with what we have with our current technology. And one way to do it is to optimize laser waveform. So what we are doing, we are thinking about waveforming, and we are implementing waveform engineering to get brightest harmonics from our plasma mirrors. So this process is a frequency-dependent process, which means that it can be enhanced by using higher frequency driving laser. For example, second harmonic of our laser would potentially generate higher harmonics. So again, we can say that the harmonic conversion efficiency or attosecond pulse intensity is a function of these various parameters, which I already mentioned before. And you can see that there is a laser frequency here. So the conversion efficiency does depend on the frequency of the driver. So, in the not so efficient regimes where this A naught over N ratio is less than 0.5, the efficiency of attosecond pulse generation and harmonic conversion efficiency, it increases with the frequency, right? We can say that the conversion efficiency in attosecond pulses or high harmonics, it's also a power law of A naught over N parameter in the less efficient regime. And if we plug our expressions for the A naught and for the N, we can see that it becomes a power law of frequency. So it's a really strongly frequency dependent process. So frequency doubling would increase at the second pulse intensity and high harmonic intensity. So, however, it is also a waveform dependent process. It's not only frequency dependent, it's also waveform dependent. It means that the particular shape of the waveform and the shape of electric fields, subcycle shape of electric fields in the laser pulse, they also strongly affect high harmonic generation. It means that this process can be enhanced by using multicolor waveforms, not just upconverted laser frequency, but laser waveforms which contain several colors. That would be even more efficient than just frequency doubling your laser, for example. And this is the approach we first have shown theoretically, and now we are pursuing it in experiment. So if you look at the intensity of the attosecond pulses as a function of energy fraction in a second color in your two color beams, for example, you want to drive the harmonics with two color beams, the fundamental frequency component and second harmonic component. So if you change the energy fraction in second harmonic, you can see that the intensity of the attosecond pulses can be enhanced for a certain fraction of second harmonic in the beam. It has a maximum. However, it can actually drop if you upconvert, if you frequency double the entire laser beam. So a combination of colors works better for improving efficiency than just one color of a higher frequency. So also extremely important is that even slight conversion into a high frequency, into a second harmonic, for example, of the order of 5% can produce significant gains in harmonic intensity or out of second pulse intensity 10 times. So we can also, that's what we know about two colors, but we can also think about optimal waveform. We can optimize the waveform to get the brightest harmonics. And we have done that in simulations, in particle and cell simulations. And we have shown that by adding colors to our waveform, the second harmonic, the third harmonic, the fourth, and the fifth, we can significantly boost the intensity of the attosecond pulse, shown here on the left side. On the left y-axis is the intensity. And initially with our laser, which in the best case has a naught of 20, around 10 to 20 watts per square centimeter in intensity, we are very low in efficiency because we are very far from the optimal ratio of A naught over N. However, by adding colors to our laser, optimizing the waveform, we can get higher efficiency than in the most efficient case with the optimal A naught over N ratio. So, which means with a very high driving laser intensity. So, and this is how the optimum waveform looks like. This red wave packet is showing the optimal waveform for our process. It contains first 5 harmonics, the fundamental and first 5 harmonics of the fundamental. If one is using optimum waveform for the high harmonic generation from plasma mirrors, more than 60% of laser energy can be converted to higher frequencies, means higher than 6 harmonic with optimum waveform. Also, in this case, when a waveform is optimized, maximum efficiency is largely independent of A naught and N of laser and plasma parameters, which is also great. We have more degree of freedom here by optimizing the waveform. All right, so experimentally, how we approach this waveform optimization in our experiments. So we try to use the plasma mirror itself as a multicolor waveform synthesizer. So we try to synthesize the optimal waveform using frequency conversion by a plasma mirror itself. So the scheme is like this. We focus our laser on a first glass target, generate plasma, which upconverts light, and then we use this upconverted light on a second target where we hope to observe enhanced relativistic harmonics. Particle and cell simulations show us that there is hope, there is a lot of hope in this process. So these are the spectra for simulations of this cascaded plasma mirror high harmonic generation, and the blue spectrum shows the high harmonics after the first plasma mirror, and the red, you see it's higher in power, in intensity. This red spectrum is generated by interaction of the multicolor waveform with the second target. All right, so let me tell you, I have a couple of minutes left, so let me tell you how we are doing this in our experiment. So in our experiment, we are actually using 3 plasma mirrors. We have a first plasma mirror for temporal contrast cleaning. So we have our few hundred millijoule, 25 femtosecond, 800 nanometer, 10 hertz pulses. And we have a first plasma mirror, which is seeing laser intensities of the order of 10 to 16 watts per square centimeter, and it works as a temporal and spatial filter, nonlinear filter for our laser pulses. So our laser pulses do not have a perfect contrast, which means that in our case, they have some pre-pulses preceding the main pulse. This is a third order autocorrelation trace of our laser pulse. Y-axis is the laser intensity, and x-axis is the horizontal axis is the time in picoseconds. So this is 500 picoseconds before the arrival of the main pulse, and the main pulse sits here. And again, this is logarithmic scale. So these are orders of magnitude. You can see that the red curve shows our initial beam. So we have a very nice contrast, intensity contrast. In this area, we don't have a lot of amplified spontaneous emission, pedestals. However, we have these pre-pulses at around 500 picoseconds before the main pulse. So this is why we are using the plasma mirror to clean them out, to get rid of them. And the blue line here shows the autocorrelation trace after that plasma mirror, and you can see that these pre-pulses are sufficiently, significantly suppressed by this plasma mirror. So this pulse, the blue pulse, is good enough for our ultra high contrast laser solid interaction experiment. So then comes the second plasma mirror. All right, I have a note, so I will wrap up quickly. So we have a second plasma mirror where we generate our multicolor waveform, and we characterize this waveform. We have direct beam diagnostics. We characterize the pulse duration, near field and far field beam profiles, and we do contrast measurement. And then after that, we send the beam to the third plasma mirror. All right, so we, as a first step, we have fully characterized the two-color beam, which was produced by a second plasma mirror. This is the spectrum in the visible range measured with the ocean optic spectrometer. You can see the reflected fundamental, second harmonic, third harmonic, and fourth harmonic. So that's a really multicolor beam. And the energies of the color components, at least the first two, are about 100 millijoule at fundamental and 30 millijoule at second harmonic. We also characterize the beam profiles, near field beam profiles, and far field focal spots to show that this multicolor beam is focusable and has a nice spatial quality, which is great, and that we can use it, we can refocus it and use it for the next interaction with the third plasma mirror. And so this is an experiment that we are doing now. At the moment, we are measuring the harmonics from the third plasma mirror, again, with the visible spectrometer, and also eventually with the XUV spectrometer. And we also characterize the beam profiles of harmonics generated by the third plasma mirror. So this is ongoing work. So as I have to conclude now, I would jump to the conclusion, and just summarize what the plasma mirror is and what are the advantages and the challenges. So the plasma mirror is a short pulse driven relativistic high energy density plasma. It's tiny, so the plasma size is of the micrometers, and the size of these relativistic electron bunches, which are generating high harmonics, is of nanometers. So it's really, really small. It's transient. The plasma formation lasts for femtoseconds. The lifetime of this plasma is of the order of picoseconds, and the dynamics of the electron bunches is on the order of attoseconds, 10 to minus 18 of a second. So that's extremely fast and transient. And this plasma is very dense. The electron density is higher than 10 to 21 centimeter to the power minus 3, and the density of the electron bunches is even higher than that, orders of magnitude higher than the plasma electron density. It's higher than 10 to 24. So these are really dense, relativistic, fast electron bunches. So this matter can only be probed by X-ray spectroscopy, including high harmonic generation spectroscopy. So it's really hard to probe this plasma, and high harmonics can help us probe it. Advantages: we have high reflectivities and high laser intensities. We can steer and focus ultra-intense laser beams with our plasma mirrors, can handle intensities much higher than 1 terawatt per square centimeter, not prone to laser damage. They can temporally specially filter laser beams. They can produce powerful X-rays and coherent harmonics. And potentially they can generate, through generating powerful X-rays, they can generate extremely bright attosecond pulses, which can approach intensity regimes relevant for quantum electrodynamics experiments. There are challenges in this experiment. You need to move a target to a new spot for each laser short. This limits the repetition rate. You need very high contrast laser pulses. You strongly depend on laser intensity. It's a very nonlinear process. So, and high intensities, they have to be achieved by extremely short focusing, which is difficult in experiment, and you require high quality focal spot. At the same time, one needs to eliminate sources of variability of harmonics. So these harmonics are usually quite variable because there are many sources of this variability. For example, beam pointing jitter, or mechanical jitter of the target surface position with respect to the laser focus. And because the process is very intensity dependent, it's very sensitive to this kind of jitter. So, and these sources have to be eliminated. Also, this laser solid interaction produces a lot of debris that, especially in the short focusing geometry, can easily damage components, optical components. Off-axis parabola is a consumable in this kind of experiment. So, all right, I just have 1 minute left. I wanted to show you a roadmap. Where are we? What is our game, and where are we really heading with these experiments? So this map shows peak power on the y-axis as a function of wavelengths, and it shows various existing sources of high peak power. For example, you can see the all these near-infrared lasers and visible lasers, for example, NIF here, with starting with the first CPA below gigawatts of power. Our system is here with 20 terawatts of power, and nowadays we have lasers as high as 5 petawatts for example, in Korea, and in the US, there are more and more lasers coming of a petawatt scale. So for X-ray and extreme ultraviolet wavelengths range, we have free electron lasers here, LCLS, and here's flash in DESI. And these are the range of powers well below terawatt power. And we have various secondary sources from laser interaction and accelerated electrons in gases. So you can see that there is an empty area here. In this parameter regime, there is a gray area. And this is really where we are heading to. So we are really have a goal of getting ultra high power at ultra short wavelengths, and with the hope to cover this gray area. So if we put our scaling, which coherent synchrotron emission gives us for the relativistic high harmonics from plasma mirrors, we can see that the scaling follows this line. So that's quite promising. This line is plotted assuming that the harmonics are driven by a petawatt laser source. So spectral power law scaling of relativistic harmonics allows for 1 terawatt per 1 kiloelectron volt harmonic to be generated. So here it gives us power above the power of current X-ray free electron laser sources. Thus, we have a hope that plasma mirrors may help fill the gap between petawatt near-infrared lasers and X-ray free electron lasers. And moreover, if we optimize the waveform and think not in terms of power per harmonic, but power in an attosecond pulse, which consists of many harmonics, right? Then theory tells us that with optimal waveform, we can boost the intensity of this attosecond pulse this way. So this is a projected intensity of attosecond pulses generated by plasma mirrors. You can see that this intensity approaches the so-called Schwinger limit, where the quantum electrodynamics effect start to be very important, and lots of new physics can be revealed. So these diagonal lines on this plot show the intensity, the power per per area of focused light. All right, so I hope I could convince you that relativistic harmonics could be an interesting and promising source of X-ray and could help fill us this gap. And with this, I want to conclude. Thank you very much for your attention. And I would like to acknowledge all the people who did the work I was presented today. My former graduate students, Matthew Edwards in the first place, who is now at LLNL, and who did a lot of work which I presented today, and contributed a lot to the development of our experiments. This is a photo from Matthew's PhD defense. Was really a highlight of my stay at Princeton. And I want to also thank my current graduate students, Nick, Andreas, Izzy, and Jesse, who are working on these experiments and theory, and researchers working with me, and technicians, and Netfish for wonderful collaboration through this years. Thank you very much for your attention.
Thank you very much for the very nice talk. So I invite people to write your questions in the chat field. And also while we're waiting for those, please also, you can unmute yourselves to give a nice round of applause. No. And many people are virtually applauding you too, you can see. So we do have one question already from Yuan Shi, who says, when you mentioned waveform optimization, how is the optimization done exactly? Can the optimized waveform always be realized in experiments?
That's a great question. Thank you so much, Yuan. Yeah, so the waveform I showed is obtained in particle and cell simulations, and we used a genetic algorithm to basically optimize that waveform by adding harmonics to the fundamental frequency, and we optimized the number of harmonics and also the phases. So the phase is also very important, the relative phase between these harmonics. So it's rather easy to do it, not so easy, but rather easy to do it in simulations. It's harder to do it in experiment, but there are ways. So one way I try to explain using the plasma mirror cascade as a way to optimize the waveform. The plasma mirror itself generates harmonics with a proper phase, so with the phase already optimized for the next interaction. The plasma mirror optimizes the phases of generated harmonics. So that's our hope, to see the enhancement of harmonics by using a multicolor waveform driven by a plasma mirror. It can also be done by different frequency conversion techniques, such as, for example, one can use nonlinear crystal to add a certain amount of second or third harmonic to the main fundamental beam, and adding just a few percent already helps a lot to increase the harmonic efficiency. In that case, it's also very important to control the phase, the relative phases between color components in the waveform.
Thanks. So I had to talk about. I had a question about the movie that you showed. Could you, just for my own edification, walk through like what happens as you go from the nonlinear, from the linear regime to the nonlinear regime, and what sets those scales, and also related the what exactly were your units on A0 and N?
Try to go back. Well, there is basically no linear regime. It's very nonlinear from the beginning.
So even if you had very weak intensity?
We do start with high intensities, right? So you mean what? Yeah, we can say that in the beginning, when the intensity is not so high, we are probably in not so nonlinear regime, right? And so, what is your question? How do we? What is?
So what would be different when if you have a much weaker intensity beam, and how does that transition occur as you ramp up the intensity? What changes? And
Right. Well, eventually you will not have this very dense ultra-short electron bunches formed. You will have some density perturbation in this plasma, and if the intensity is as low as, for example, 10 to 16 or 10 to 17 watts per square centimeter, you will basically reflect the fundamentals. So the plasma mirror will really act as a mirror. So just mirror without frequency up conversion. But if you start increasing intensity above 10 to 17 watts per square centimeter, you will see more and more harmonics coming. So first you will see some second and third harmonic, and then as these electrons will get denser, shorter bunches, and faster, as their speeds will go up, they will become more and more relativistic. You will see higher and higher harmonics. Does this answer your question?
yeah, thank you. And there's a question from Ginia Bogman. To the extent that you can measure it, to what degree do experiments agree with PIC simulation predictions? To what extent would you expect simulations experiments to agree?
That's a wonderful question. So in simulations, of course, we have a lot of parameters we feed in, and not all of these parameters we know in our experiment. So we always can find a simulation which could fit the experimental data, but we don't know all the parameters. So we know the we can estimate our laser amplitude, knowing the laser energy and pulse duration and focal spot size. we can estimate the plasma density, but we don't really know exactly what is the density gradient. We don't measure it yet. In experiment, we just can guess what is the highest plasma density in the target. So this is why the for higher order harmonics, the direct comparison of simulation and experiment is not easy because there are some parameters we don't know for sure in experiment. But we have a pretty good agreement, actually really excellent agreement for low order harmonics between simulations and experiments. So for like second, third, and fourth harmonic, the intensities of these harmonics generated in experiment, they agree very well with the simulations.
Thank you very much. And I guess I'd like to thank our speaker again. Please, if you want to give her another round of applause. And I hope everybody has a great rest of your Thursday. And thank you again for giving this talk.
Thank you so much. It was really a pleasure to be here.